Alright, so this is section 5.4, differentiation of exponential functions. So in the same way that we differentiated logarithmic functions, we're going to have formulas to differentiate exponential functions. And in this case, these ones, most of these are going to be like very straightforward formulas, especially when you have the derivative of e to the x, which is itself e to the x. There's no change at all. We don't do like in the natural log function 1 over x and that's it. No, this is simply e to the x. Of course, we have the other extension when we have something more composite like e to the some algebraic expression and like e to the u. Well, all we do is differentiate e to the u, which is itself times the derivative of whatever is in the exponent of the exponential function. All right, let's look at some examples to illustrate this, the use of this the differentiation of exponential functions. So the derivative of f of x equals x cubed plus e to the x, f prime of x equals 3x squared plus the derivative of e to the x, which is itself e to the x. There's nothing further to do over here. That's it. For letter B, we're going to use the product rule. So in the same way that we did the product rule for the previous section. So let me write down what the product rule is. So u v prime, that's a u prime v plus a v prime u. And in this case, well, y prime equals the derivative of x cubed, which is 3x squared, times e to the x, plus the derivative of v, which is the second factor, e to the x, but in this case, the derivative of e to the x, it's itself e to the x times x cubed. And we're essentially done with the calculus here. However, we can simplify this a bit further. Notice that in this case, we have a greatest common factor of number 1, x squared, and e to the x. If we factor this out, we're going to be left with 3 plus x. So that's final answer. For letter C, let's use the chain rule in this case because we have a composite function of a radical, an exponential, and then we have a polynomial in the exponent of the exponential function. However, let's rewrite this e to the 3x squared plus 9 as whole thing to the 1/2 power. And in this case, let's use the chain rule, that is y prime equals 1/2 times whatever is inside of the parentheses, which is in this case e to the 3x squared plus 9, times 1/2 minus 1, which is in this case negative 1/2. However, because of the chain rule, we need to differentiate this with respect to x. And when we differentiate this with respect to x, so okay, at the same time, I'm going to do the following. I'm going to do 1 over 2 e to the 3x squared plus 9 to the 1/2 times the derivative of e to the 3x squared plus 9. The derivative of the exponential part is itself e to the 3x squared. The derivative of 9 is 0, and then we still do one more chain rule to differentiate the part of the exponential, which in this case the derivative of 3x squared, that's a 6x. Whoops. Alright. However, notice how in this case 6 goes into 2 3 times. And I'm going to multiply 3 times the exponential and leave it in here. 3 e to the 3x squared. The whole thing divided by e to the 3x squared plus 9. And instead of using the rational exponent notation, we're going to go back to radical notation. So here was a problem in which we applied the chain rule to different, but now including an exponential function in it. All right, let's look at another example. Let's look at letter D. e to the negative x squared times ln of x squared plus 2. So in this case, we're going to combine logarithmic functions with exponential functions, which is possible. Why not? Of course. So number one in this case, so notice in this case we have the combination of a product rule, and each individually will have a mini chain rule when we differentiate each of the terms. So let's go ahead and write the product rule again. Well, let's use the product rule. That is, okay, let me rewrite it again. So that's the derivative, or that's uv prime. That's u prime v plus v prime u. So let's take the derivative of the first factor, the derivative of e to the negative x squared. So in this case, so that's a y prime equals itself e to the negative x squared times the derivative of negative x squared, which is negative 2x. But that times ln of x squared plus 2. Okay, just to label, let me just label just to show you what we're doing. So this is the u prime, this is the v, and then let's take the derivative of ln 1 over x squared plus 2, ln of x squared plus 2, and that's times 2x, which is the derivative of x squared plus 2, and that times e to the negative x squared. In other words, what do we have here? This is v prime u. So that's the product rule applied to the derivative of this function. And well, in this case, let's use some algebra to simplify all this. By the way, there's really not that much to simplify, other than, let's see if there's anything interesting to simplify. Okay, so I'm going to factor out the 2x, and I'm going to factor out the e to the negative x squared. Those are the GCFs over here. I don't think there's anything else to factor any further. And in this case, well, so that's going to be 2x times, and that's going to give us a negative ln of x squared plus 2, plus, in this case, that's going to be 1 over x squared plus 2. All right, and we could leave it like this. Oh, I forgot the exponential factor. Okay, let me write the factor over the exponential over here. Or we could rewrite this instead as a 2x e to the negative x squared